You are watching part 2 of the Control educational video series, Process Control Basics, Flow Measurement. This video is brought to you by our sponsors, KROHNE, Badger Meter, and Endress+Hauser. More information about our sponsors will be provided later on in this video. Our presenter today is Editor-in-Chief of Control Magazine and ControlGlobal.com, Paul Studebaker.
Flow rate is among the most commonly measured and controlled process variables, so a broad range of flow measurement technologies have been developed over time. These technologies measure flow by measuring physical properties and dynamic characteristics of fluid in motion and correlating those measurements with flow rate. Each of those flow measurement technologies has its advantages and limitations, and an application is typically driven mainly by compatibility with fluid characteristics and process conditions. Secondly, by overall performance requirements, and thirdly, by cost. Good flow meter selection depends on a clear understanding of the requirements of the particular application. Spend the time up front to fully evaluate the nature of the process fluid and the installation. Use a systematic step-by-step process to develop the specifications. In applications where products are bought and sold on the basis of a meter reading, absolute accuracy is critical. In other applications, repeatability may be more important. In general, reliability is higher for flow meters with no moving parts. With a few exceptions, the accuracy of most flow meters will be affected by density, pressure, and viscosity variations. Also consider intangible factors, such as technicians' familiarity with the technology, their experience with calibration and maintenance, and spare parts availability at the site. The cost of the installation should be computed only after taking these steps. One of the most common flow measurement mistakes is attempting to justify the use of a technology because the device itself is less expensive. Consider the installed and life cycle costs. So now let's take a tour of some of the most common and useful flow meter technologies. Orifice plate flow meters infer volumetric flow rate by measuring the difference in pressure before and after the fluid passes through a restriction. The restrictions, called flow elements, come in a wide variety of configurations, each with specific application strengths and weaknesses. But by far the most common example is the orifice plate, where fluid passes through a precisely machined opening concentric with the inside pipe diameter. If fluid density is known or can be calculated from pressure and temperature measurements, a mass flow rate can be inferred. In a rotometer, or variable area meter, the force of the flowing fluid moves a weighted float upward in a tapered vertical tube. The higher the flow rate, the higher the float's equilibrium point. Advantages include low cost, simplicity, low pressure drop, wide range, and linear output. If only a local display is needed, no power is required as the float position can be seen through a transparent tube. The float can be magnetically coupled to a dial indicator, or an electronic transmitter can be used to send flow rate information to a remote display or controller. Differential pressure and rotometers both restrict flow to cause a pressure difference. One advantage of magnetic meters and ultrasonic meters is that they don't restrict flow. The magnetic flow meter, or magmeter, works only with conductive liquids such as aqueous solutions. It consists of a non-magnetic pipe lined with an electrically insulating material. As shown here, a pair of coils generates an electric field, and the motion of the conductive fluid through the field generates an electric potential, a voltage, between the electrodes, proportional to the velocity of the fluid. Ultrasonic flow meters measure fluid velocity by measuring the effect a moving fluid has on the speed of sound. Transit time, or time of flight, meters measure the phase shift between upstream and downstream transducers and are used primarily with clean liquids and gases. Doppler effect meters rely on a single transceiver and measure the frequency shift of sound waves reflected from suspended particles or bubbles within the flowing stream. Frequency-based technologies include vortex and turbine flow meters. Vortex meters use piezoelectric sensors to gauge the frequency of vortices shed from turbulent flow around an in-stream shredder bar. A piezoelectric sensor detects the pressure oscillation around the bar, or a piezoelectric strain gauge detects the forces exerted on the bar. The vortex shedding frequency is directly proportional to the velocity of the fluid in the pipe and independent of fluid properties such as density, viscosity, and conductivity. The flow must be turbulent, so a zero reading on a vortex meter doesn't necessarily mean zero flow. A turbine flow meter consists of a multi-bladed rotor mounted at right angles to the flow and suspended in the fluid stream on a free-running bearing. The diameter of the rotor is very slightly less than the inside diameter of the metering chamber, and its speed of rotation is proportional to the volumetric flow rate. Turbine rotation is detected by solid-state devices or mechanical sensors. The final two technologies that we'll talk about on our tour are mass flow meters, so named primarily because of their relative insensitivity to variations in temperature, pressure, and other process conditions that can significantly affect the mass flow rate calculated from a volumetric device. The Coriolis meter takes advantage of the phenomenon that Gustav Coriolis first observed as the tendency of bodies moving on the surface of the Earth to drift sideways because of the eastward rotation of the planet, to the right of the motion in the northern hemisphere and to the left of the motion in the southern hemisphere. When mass flows through a vibrating tube, Coriolis forces will tend to twist the tubing. By measuring the magnitude of displacement caused by this twisting force, the Coriolis meter can directly calculate mass flow rate. Our final flow meter is the thermal mass flow meter, which measures the mass flow rate of gases and liquids by introducing a known amount of heat into the flowing stream and measuring an associated temperature change, or by maintaining a probe at a constant temperature and measuring the energy required to do so. They are often used for monitoring or controlling mass-related processes, such as the chemical reactions that depend on mass flows of ingredients.
Thank you for watching part 2 of the Control Educational Video Series, Process Control Basics, Flow Measurement. This video is brought to you by our sponsors, KROHNE, Badger Meter, and Endress+Hauser. Company and product information is provided in the information section below. The KROHNE Coriolis mass flow meters are targeted at the oil and gas and petrochemical industries. Typical applications for the new large line sizes include bulk hydrocarbon loading and bunkering, LNG, cryogenic, or high temperature applications. They feature gas and liquid MID and OIML custody transfer approvals and compliance with API and AGA guidelines, SLIN 2/3 functionality, and NE 107 diagnostic functions. The Badger Meter TFX 500W transit time ultrasonic flow meter measures the volumetric flow of clean water in pipes 10 inches or smaller. By clamping on the outside of the pipe, the ultrasonic meter installs without cutting or tapping the pipe. Features include a clamp-on non-invasive flow meter, a bidirectional flow measurement system, and measurements of the flow rate, including total and velocity of water flow. The Endress+Hauser PicoMag is an economical mag meter for conductive liquids in many industry applications. Its space-saving design and easy installation make it perfect for end customers, skid builders, equipment manufacturers, and system integrators. Additionally, its future-oriented intuitive operation via the Smart Blue app ensures fast, secure, and simple commissioning.